Now, instead of actually drawing the direction field, it would be much easier if we could find an algebraic formula to give us the actual values of these points along this approximating curve that we get from Euler's method. So remember, Euler's method is going to make precise this idea of following the arrows, and we're talking about an equation y prime is f of xy, where that f of xy is some formula in x and y, and we're looking for a solution which satisfies the initial condition y of x naught equals y naught. So we're going to generate a table of approximate numerical values of y for specific values of x in the interval from the starting point x naught to some point b. And this is called a numerical solution to our problem. Let's look at the problem that we looked at in Mathematica, estimate y of 4, where y of x is a solution to the differential equation y prime equals y minus x, satisfying this initial condition y of 2 equals 0 on the interval from 2 to 4. So Euler's method approximates the path of the solution with this series of line segments following the direction of the arrows in the direction field. And the first thing we want to choose is the step size, which is going to be the change in the x value along each arrow that we use in our approximation, or each line segment that we use in our approximation. And in general, a smaller step size is going to get us a better approximation. And we're going to use h equals 0.2 as we did in the Mathematica demonstration. So our starting point is here at x naught, y naught, where x naught is 2 and y naught is 0. And our starting point always comes from the initial condition in the problem, y of x naught equals y naught. So for us, x naught is 2 and y naught is 0 because our initial condition is y of 2 equals 0. Now, as we saw in the Mathematica demonstration, the green curve is the actual solution, and the red curve that we're going to generate here is going to be our approximate solution. So to get to the next point on the curve, we follow the arrow in the direction field, which starts at x naught, y naught, and its slope, of course, we know is f of x naught, y naught. We stop when we get to the point where the x value is x naught plus h. Now we can figure out the actual point at the end of this arrow. We know its slope f of x naught, y naught from the differential equation. This is if our differential equation is y prime equals f of xy, then this is the right-hand side of the differential equation applied at the initial point. And that's the slope of this arrow. But we also know that the slope of the arrow is the difference in the y values divided by the difference in the x values. And the difference in the x values we're controlling, that's h. x1 is x naught plus h, and so x1 minus x naught is h. So now we have an equation where we know absolutely everything except the y value at the end of this arrow, which we're calling y1. So if the point on the end of this arrow is x1, y1, then y1 can be figured out from this equation. It's y naught plus h times f applied to x naught, y naught, the initial point. So for example, in our particular example where y prime equals y minus x, f applied at the initial point is f of 2, 0, and that's minus 2. And x1 is 2.2 or 2 plus 0.2, and y1 is 0, which is y naught, plus h times minus 2. So it's 0.2 times minus 2, which is minus 0.4. And now our next arrow starts at x1, y1. We know the coordinates of x1, y1. We can go through exactly the same process to find the coordinates of the point at the end of the second arrow, which we're going to call x2, y2. And there's no need to reinvent the wheel. The formula is going to be exactly the same because the process is exactly the same. So x2 is x1 plus h, and y2 is y1 plus h times f applied at the beginning of the second arrow, so f applied at x1, y1. And of course, the second line segment of our approximating curve is the line segment joining the end of the first arrow and the end of the second arrow. Basically, it follows the same path as the second arrow. We can just carry on with this process and get the exact coordinates of these endpoints that we use to approximate the solution curve. And we can draw a picture if we like. We can draw those endpoints and join them with straight lines, and that gives us a picture of our approximate solution. So we repeat this process until we get to the x value of interest to us, where we want to approximate y of a. And if we want to go from x0 to some point a, and we want to approximate y of a using a step size h, then we have to use a minus x0 over h steps. So we should use an h so that that's an integer, so that we have an integer number of steps. In our approximation to a solution to y prime equals y minus x on the interval from 2 to 4, we would have liked an estimate for y of 4. And we started at the initial point with x0 equals 2 and a step size of 0.2, and we're going to get our approximation in 4 minus 2 over h steps, and with h equals 0.2, this is 10 steps. So we have to apply this algorithm 10 times to approximate y of 4, and that's exactly what we're going to do. We're going to apply the algebra without bothering with the picture. Note, as we did in the Mathematica demonstration, how this red approximation to the curve deviates a little more from the actual solution as we move away from the initial point, and if we chose a smaller value of h, it would stay a little closer. So to get our approximation to the solution of y prime equals f of xy with an initial condition y of x naught equals y naught, we're going to use n steps, and we can decide what that n is by dividing our interval into n equal parts. And our series of approximations is given by the initial point, which we read from the initial condition, x naught, y naught. And the next point in our approximation is x1, y1, where x1 is x naught plus h and y1 is y naught plus h times f applied to the initial point. And the next point on our approximate curve is x2, y2, where x2 is x1 plus h and y2 is y1 plus h times f applied to the previous point, x1, y1. And in general, if I have a point in my approximation, xi minus 1, yi minus 1, the next point on the approximating curve is going to be xi, yi, where xi is xi minus 1 plus h, and yi is equal to yi minus 1 plus h times f applied to the previous point, xi minus 1, yi minus 1. So if I want to use Euler's method with step size h equals 0.2 to find an approximation for y4, where y is the solution to the initial value problem y prime equals y minus x, where y of 2 equals 0. I start with my initial point x naught y naught equals 2, 0, and I generate an approximate solution joining 10 points in the interval between x equals 2 and x equals 4. And of course, the final y value after this 10th iteration of Euler's method will give me an approximation for y of 4. X naught, y naught is the initial point along my approximate curve, and that's 2, 0. And the next point is what I get by applying Euler's formula for x1, y1. x1 is x naught plus h, which is 2.2, and y1 is y naught plus h times f applied to x naught, y naught, which is y naught minus x naught. So x1, y1, according to the formula, is 2.2 minus 0.4, and then I get x2, y2 by applying my equations to x1, y1. So x2 is x1 plus h, which is 2.4, and y2 is y1 plus h times y1 minus x1. And I carry on in this way until I get to a point where x equals 4, and then I have an approximate value for y of 4 to the actual solution to this equation. And keep in mind that this is an approximation. This is not the true value of y of 4 for the solution to this equation.